Welcome everyone. We had the opportunity to join the launch campaign of the Stratos IV rocket, where Sebastian is working on the recovery section of the rocket. He had a couple of minutes time to give us an idea of what the entry, descent and landing system of the Stratos rocket looks like. Welcome Sebastian, great to have you here. Could you give us an introduction of who you are and what Project Stratos is?
Yeah, so thanks for inviting me, Thomas. So my name is Sebastian Oliver Scholts. I'm currently the Chief Recovery of the Stratos IV project and a master's student at TU Delft. The Project Stratos is a project that started about 3 years ago, where we want to build a rocket fully done by students to reach and break the European altitude record, the student altitude record actually. And yeah, we want to do that by building a hybrid engine rocket.
Oh, very impressive.
Yeah.
So how does the recovery system specifically of the Stratos IV rocket work?
Yeah, so we use quite a few different systems for recovery. We first want to ensure that all of the internals of the recovery bay and the nose cone stay intact. So we use a heat shield to pretty much protect the internals during re-entry, during the heating phase. Then we deploy a drogue parachute. So we use a Hemosflow ribbon parachute for the drogue parachute. And then afterwards we deploy a main parachute after it's stabilized. And then this will pretty much slow the capsule down to about 70 kilometers per hour and it will touch down in the sea.
Oh, great. So what kind of materials will we be using for the parachutes?
For the drogue parachute, we'll be using mostly aramid-based materials. So we use Triron for the canopy of the parachute, and we use Technora for the suspension lines and rudder lines. And then for the main parachute, we use mostly F111 nylon fabric for the canopy, and we use Spectra suspension lines, and also some nylon for the riser as well.
Good. All very high-strength materials, especially
Yes.
for the drogue.
Yes.
So you mentioned the drogue parachute, that it will slow down the capsule to velocities where the main parachute can be deployed.
Yeah.
But will you be deploying the drogue parachute at supersonic conditions?
For our case, no. The Hemosflow ribbon parachute that I mentioned that we use for the drogue parachute, it can be deployed supersonically, as a very wide range of Mach numbers that it can operate in, also dynamic pressures. But we saw that during our simulations that the nose cone is quite unstable during descent, and it will enter a flat spin, so it'll tumble. This will also bleed the velocity down a lot, which we saw that it would be more beneficial to deploy the drogue parachute subsonically, so at a much lower height. This will avoid certain flow phenomena that occur during supersonic and even transonic regimes.
That makes sense. Why use the high-risk scenario where you can keep it safe?
Exactly.
That makes
Yeah.
sense. So what kind of deployment devices do you use to deploy the drogue and the main parachute?
For the drogue parachute, we use a mortar system, which we call the hot gas deployment device. It produces a very hot gas using nitrocellulose and some black powder for the igniters. We have a certain plenum volume that allows the the drogue parachute to deploy around 18 meters per second. This allows the drogue parachute to be deployed without being entangled, as the capsule will be doing a flat spin. And then the main parachute will be deploying using a very simplified spring system. This is because the drogue parachute will stabilize the vehicle, and therefore it will not be going down in a flat spin. And therefore we just went with a very simple spring system just to deploy the main parachute around maybe a few meters per second, maybe 1 or 2 meters per second, and just to keep it simple.
Oh, that makes sense. Do you use sort of a pilot chute for either the drogue or the main parachute, or do you just rely on the deployment devices themselves?
For the drogue, we don't use any pilot chutes. We attach the lid that pops out of the canister to the parachute bag. This will ensure that the momentum of the lid will take the parachute out of its bag. But for the main parachute, we use a fairly big pilot chute just for to ensure that the main parachute really gets out of its bag, and that's that.
Oh, interesting, very interesting. So what kind of testing methods have you used throughout the years to prove that these parachutes work, or prove that these deployment devices work?
Yeah. So for the motor, we did a lot of different tests. We first tested using a battleship canister. This was just to test the proof of concept and see if it was actually feasible. We had very successful tests with those. Also to measure the internal pressure and the ejection velocity that we get by varying the amount of nylon bolts that we use for the lid. And for the main parachute, we did a tabletop test deployment where we just removed the parachute out of its bag by pulling it out of the canister, and we've also just had the whole system assembled and then just cut the wires using a pair of scissors and seeing how well that would eject the main parachute. And so far those tests were all successful. And not only that for the deployment systems, but for the parachutes themselves, we validated them in the wind tunnel by assessing their stability performance at subsonic conditions.
Oh, great that you can use a wind tunnel.
Yeah.
Great resource.
Yeah.
So have you always used these types of parachutes for previous Stratos missions as well, or did they use different types of parachutes?
So for the previous Stratos mission, Stratos IV, we used the same drug parachutes, it's the same Hemosflow ribbon design, same size and same shape, and we didn't see any need to change this design. But for the main parachutes, we changed from a cross parachute for Stratos III to a disc gap band for Stratos IV. The biggest reasoning is because testing, the cross parachute is very unstable, and it was very hard to get any quantitative data from it. And we just saw that a disc gap band was a lot more stable, allows for a little bit better drag performance at a bit of a cost of volume, but we saw that was perfectly fine and we went for the disc gap band.
Great, yeah, the disc gap band is a beautiful parachute.
Yeah, it is.
Completely agree on that point. So how do you plan to find the rocket nose cone back after it has landed safely in the ocean?
Yeah, so for our final phase during flights, we have the retrieval module. From our simulation data, we saw that we will be quite away from the coast, so the nose cone will land quite far away. And therefore we use an Iridium module. So this is the active retrieval system. The Iridium module will give us an approximate location of where the nose cone is. And then we will navigate with the boat to the area where we have the location data and start a search pattern. And meanwhile, once we're in the vicinity of where the nose cone has landed, we will then look out for the passive system that we use on the nose cone, which is 3 strobe lights. So these are 3 water activated lights, which is mainly useful for night retrieval. And we also have fluorescent dye in water soluble bags that will also help us to locate the nose cone.
Oh, great to hear that you have multiple options to find this nose cone back.
Yeah.
Quite an endeavor. As a final question, also for the viewers, when will you be launching the Stratos IV rocket?
Yeah, so yeah, that's a good question. We'll be launching around the middle of October, so it's coming up very soon. So make sure to keep up on our DARE social media on Facebook, Instagram, and LinkedIn, because we will be live streaming it, and we definitely hope to see you there.
Great to hear. It's great to see that you're all working so dedicated on this project.
Yeah.
We as Chutes will be following carefully along with your launch campaign, and we'll be excited to see the launch. Thank you for spending the time with us, and good luck during the coming weeks.
Thank you.